Okay, so welcome to today's lecture in neural networks and deep learning. We started with this topic a bit last time when we talked about transfer learning, and we'll continue that in some direction. That we especially will focus on the first part. We told that you need in order to generate this initial model, you need a lot of training data, and that's typically a challenge. And therefore, what is currently their state of the art is what is called self-supervised learning, in a way that we are trying to generate artificial tasks where we then have the data without extra human effort and then can train our models on that. Maybe the most prominent example of this is at the moment language models, which do that. They're trained on just pure text which you have out there, and you're inventing a task that you can do to do that. And that will be the main topic of today. So what we're doing is we'll start with motivating this and why we want to do that. Then we'll mainly introduce the two main tasks that you can mainly do in self-supervised learning, a bit on compression, and autoencoders, and then mainly we'll focus on prediction. And then in the second part, we'll look at the three main application areas of that. We'll talk quite long about language, different language models, or models to model language that can be trained that way. Then we're looking at audio and as image to the end. But let's start with the motivation. So why we are doing it. So again, what we're doing is our general pipeline of building AI systems, where we do data collection, then we're inventing some nice architecture, and then we're training. However, what is the main challenge and what we're trying to address today is that this data collection, I mean, mainly if you're doing research at the university, you're often can just build on that other people collected good data, but typically that is an essential challenge. So how can we find the real right data that we want to learn? And if you really want to build big models, and we saw that's a big advantage of AI systems, that you can, of neural networks especially, that you can just get better in training on bigger models and more data. Of course, this is a challenge, because in a lot of tasks, you will not be able to collect huge amounts of data. So the question is, what can we do different? And last time we started this with transfer learning, where the idea is, okay, if it's really expensive to learn or to collect all this data that we need for this specific task we are interested in, maybe we can also do it in a different way. So instead of collecting always tons of data for each task that we're interested in, we're trying to train a model on other data. We are learning things on data which we have there, and then later we more have to learn only the delta. So how to get from the model trained on one data to the model on the other. That is, of course, now interesting is in the initial model, we're not really interested in being really, really good at the data that we are in this model. So you're not interested in having a really good model on that. What we're really interested in is we're learning some good initial model that we then can focus on and further. We did that a bit in this meta-learning based approach, where we're not really trying to optimize to be good at any task that we're training on, but we are more trying to build a model that afterwards you can fast train the thing. So the question is, what is our goal in the first initial step? So when we're training our initial model, what is the goal? I mean, normally that is clear. If you train a model, you want to be good at the task. But here it's a bit different. So what we want to learn is some of the underlying hidden structure of the data. So if you want to learn, if you want to do something on language, you want to somehow learn what language means, where there's ambiguities in there, how you can phrase things differently, which things mean something different, which means the same. or an image, you want to maybe do an abstraction on what is really on the image, and so that you can later build a classifier. So the goal here is really to learn like some good hidden representations that you can then easily adapt to the further thing. And that is here the interesting thing. I mean, that is why transfer learning works good at neural networks, that we have these intermediate representations layer of the hidden representation. Maybe they weren't really there at the beginning, but when you stack all the layers, you get that as a byproduct. And I mean, the interesting finding is that you can transfer them. So if they really learn some type of abstraction, so maybe in the lower layers, they first identify in language something like what are the general classes, and then they do more and more fine-grained analysis. So the question is, how can we learn these types of hidden representations? And this is the main idea in semi-supervised learning, telling, oh, maybe we don't need to learn that real task where people are really interested in. I mean, machine translation might be a task. You, I guess, all have used this in some point. Or if you think about image classification, image into what is on the image is a task which is really useful, and you have the end product. But in order to learn this representation, you want to get a better understanding of the image, and then maybe you can come up with some signal which is just natural occurring. Then you don't have to like collect the data, because normally tasks that you are really interested in, that's expensive to label because people really have to do the work. On the other hand, if you can just take images or you can just take text, by now there's luckily a lot of that available, and you can just train them in a self-supervised way. And that is why we're looking today. So we can, for example, try to look into compression. That is one idea. If you have an image and you compress it into a more tight representation, and then you make it again, try to reconstruct the image, the hope is that you'll learn a representation where some of the most important points are in there, because otherwise you can't do a good reconstruction. And therefore compression might be a good algorithm, or like a good training signal, in order to learn what is really important there and extract that. Another thing is prediction. So that is what is even currently more famous. In order to predict some properties of the image or of a text, you might need to have a quite good understanding. So we can try to remove properties, we can try to remove some part, change it part, and then ask it, okay, can you undo that? And in order to undo that, you often have to have a good intuition of what is in there, and that is exactly then the task that we're learning. And in self-supervised learning, it's always a task that we want to learn these representations, this initial model which generates good representations, so that you can then do in the next step, you can learn a very good model on top of that. So if we're going back, so where is self-supervised learning used? Of course, or at least in most cases, self-supervised learning themselves is not yet the end goal. So that is not easy what you want to have. What you want to do is you take your initial model, then you do self-supervised learning to get then your initial model. And then you'll do like supervised model with your task data and can do that. So there's the self-supervised learning in the transfer-based learning is done here. And then the supervised learning you do afterwards. And in the initial model there, you're interested in learning these types of representations, which are somehow helpful to learn then more complex other things. To get it a bit more maybe concrete, here are like two examples on natural language processing and image. So the idea is, you know, these type of models, hopefully a bit. So imagine you have a text, I live in Karlsruhe, and then in the self-supervised learning, what you really want to do is you have some type of network and you want to learn that here the representation. Maybe if it's more like a sequence labeling, you want to learn a good representation, meaning a vector for each word, which somehow represents what this word means in this sentence. And then you can do later further processing on that. And similar in image, you want to learn some type of vector here, which represents the most important features of this type of image. If you have that, then you can now, with transfer learning in the second step, like learn on top there with supervised learning a classifier. Maybe that's like some sentence classifier saying this is a fact or is a question or whatever task you want to do. So you can add then, based on these representations, you can learn this model. And of course, the main motivation is that learning this classifier from these hidden representations here is easier than learning it directly from your initial model. So your model should be able to learn representations where then further tasks can easily be trained on. So we have to, if we're thinking about self-supervised learning, what we have to think about is how can we learn representations here so that other tasks are later easy. And the same for image. So you can, of course, build directly a classifier which takes an image in there and then says whether that's a cat or a dog. But if it's a huge image, it might be very difficult. It's not easy to, like, just based on the pixel values, recognize whether this is a cat or a dog. So the idea of self-supervised learning is that we're learning a representation in between, that then this type of classification is a lot easier. So we need only limited amount of data there in order to train this type of model. And yeah, that is then mainly the conclusion of this motivation is, so in self-supervised learning, the aim is, can we define tasks so that we learn good representation? Of course, good representation is now a very ambiguous term. In our thing, it means that afterwards, it's easy to learn tasks we're really interested in based on this representation. So easy means we need less data to have a good quality in some way. Good. Yeah, with this, we can then have a look at the first bigger question and look at compression, task, and mainly autoencoders. Before we're doing that, do you have any question about the general idea of self-supervised learning? Good. So the general setup in the compression task is that, yeah, we represent our image input here. And the output of our network is also the input. So that is a different. Normally, we add as input an image, output a class, or text as input and text and some classes as output or other text. Here, we can make it, and therefore to not really need any annotations, we're just making the input and the output the same. So what we're trying is, you try to learn something that if you input something, the same thing comes out. And that, of course, is now good from the training perspective. This is just available in significantly amounts. You only need no images. You don't need images with annotations. You only need text. You don't need text with classes, translations, or anything, which is a lot harder. You just put in text and try to get text out again. And that is done, for example, in autoencoders. There is similar things in audio, for example, also for bottleneck features was famous for some time. Again, the idea is you put in audio and you're trying to reconstruct the audio out there. So what we really want to do is we want to train this reconstruction. We have our input representation, which is a d-dimensional vector. Then we're having our hidden representation, and then we have our reconstructed input. And the first question here now is, how are we doing that? So how would you train this type of model? Any suggestions? We have our input X, we have our prediction, we have the reference, which is also X. So what do you need to do? Yes? Yes, so you can just do normal reconstruction loss, mean square error, measuring the difference between our input, which is also the reference output, and the predicted one, and then we can train it to minimize that. So we want to minimize that what the model predicts is the same as the input. That would be like the first type of solution. So that seems to be very easy. It's exactly as we have our the same as we had before, where we train the model. It's just like that we are now using as our output also our input, but the training otherwise is exactly the same. If we're doing it this way, does anybody see problems or things we should consider? Yes?
Depending on the model, if you just try to approximate the average.
Yes, but if it's approximating the average, it still would have a decent loss, and maybe you get better if you're a bit better than that. Yeah. Yes?
Or if the architecture is not chosen correctly, it could learn to just bypass the values and try not to learn anything at all, but just pass from input to output and does not learn what actually is shown.
Yes, exactly. So I mean, we're saying it's compression. So we have to somehow enforce that it's really compression. So if we would take the hidden representation, the same say as our input, W1 and if W1 and W2 is just identity metrics, well, we would have a loss of 0, but we wouldn't have really learned anything. So what we just would have done is that we are learning H should be the same as X, and this is not really helpful. And because what we're interested in is not, I mean, we are forcing things with a loss, but we're really interested in these hidden representations. So if they are not trying to extract anything, again, think of how you're using it. You're like just using the hidden representation instead of your input. If they are the same, the task didn't get easier. So we have to make our task in the transfer learning for the task easier, and therefore doing our task based on these hidden representations that we're then using should be somehow more easier than with the original input. So we have to like somehow design our autoencoder in a way that this task is more challenging. To just remember things when it's just like staying everything the same is not a challenging task and therefore not helpful. So any suggestions how you could make things more challenging here? Yes? Yes, so that is the most straightforward, and that is the basic type of an autoencoder. If our H is smaller than D, then we cannot just copy things. So we have to reduce things, and then it's really a compression task. And then we are learning here really like some type of new representation that is hopefully more meaningful and that we can then use because it's like more condensed. And that is like some of the default type of autoencoder. And then, of course, W2 gets more difficult. So we somehow have to compress things and then have to like have the decoder which like reconstructs the input from this more dense representation. And yeah, I mean, the loss is still the same. So the only thing we have to do is like on this type of representation, we are trying to add some things so that it's like possible to do that. Other ideas, what you can also do?
Roll noises.
Yes, yes. Just from the slides, I have one thing in between, but I'll come to the noise. And then the other one is like to have sparsity, which is very much related to the lower dimension. Instead of like having a fixed dimension, what you can also do is like say, oh, but you're not allowed to have like everything here used, but yeah, most values should be 0. And how can we enforce that? We can just have additional loss, which tells us prefer solutions where most of the values here are 0, And then again, you have to somehow extract what is more important because you cannot just copy over. Then your loss will be very high because your sparsity is high. So the other way of enforcing like a more shallow representation is not hardly cutting things out, but just forcing that in each model you're only allowed to use 2, 3, or X number of features. And then the other thing is what you said, okay, we can just make our task more difficult. We're already going a bit then in the prediction thing. So because what we are mainly doing is we're changing our input. We're saying, yes, we want to have the output, but we are making the task more difficult by adding some type of noise to the input. And then the model does not only like no longer just cannot copy over it because the output is no longer the correct solution. Now you have to like somehow learn how a typical CAD looks like if there's like error, like some black points in there, and you have to remove them. Or if there are just some random words changed, then you have to remove them and be able to reconstruct the real image. And of course, for that, there might be more understanding necessary to do that. Yes?
So you think dropout as noise will also work?
Yes, so dropout is I mean dropout is just another way of yeah, I mean that's a good point. But yeah, I mean dropout, you put the noise, not you model it not directly at the input, but more at this, but it would be a very similar effect. I'm not daring to say now exactly the same. Maybe there are some details which are different, but it would be mainly have the same effect because again, you cannot just copy things over. The easy solution, the loophole solution we had before, where just do the identity, that is not possible. This is something in generally, if you do artificial tasks, you have to be careful that you're not doing an artificial task where there's some very easy solution which you can solve and which then makes this not learning a meaningful thing. Because always we're not really, I mean, sometimes if you're doing an artificial task, you are easy to get a perfect solution, but it's not what you really want to do because you're not interested in having a low loss here. You're interested in having a meaningful representation in there. Good. Any more questions to compression? Good. Then we already have a bit like the step over into prediction. So we said like, yeah, if you add noise to that, that's some type of prediction, and we're coming, some of the predicted models will be similar in some way to that, or to the masking even. So one example to do that is, or motivation first, why prediction is interesting. Let's have a look at text. So if you have the starting of a text, which is the plane, then one prediction task is predict the next word. So what would you say are possible connections, possible extension of this starting of a sentence, the plane? Any suggestions? Yes?
Nice.
Flies is a very good one. I guess most people have it. There can be, of course, some more. It's not a super easy task. It can the plane arrives. It can be the plane that. So you can have a subclause, but flies is a very, very good or probable thing. And that makes things easy because in order to have this, if you have to think about it, so we said typically in language there's maybe 100,000 words. So if you have no idea about text, the next word, you have a chance of like 1 divided by 100,000 that like each word would be equal distribution. But with your world knowledge, with your knowledge about sentence structure and so on, there's a lot smaller like possibilities of what is correct there. The plain Karlsruhe is already a bit, I mean, it could be the name, but it's already a bit hard. But there is a lot of knowledge that you can use in order to predict and have a good estimate of the next one. And that makes this task so super interesting because you need to have, on the one hand, semantic knowledge in order to have a good estimate what could be the next word. The plane drives is a bit awkward sentence, so that's not very, very high probability. There you have to have syntax. So it can be this, afterward there's a verb or a starting of a subclause, but or like a preposition of, but the plain the isn't a good sentence. So you have to have in this, if you want to have a very simple task, you're just predicting the next word. There is a lot of knowledge that you have and understanding of the text to do this task at a good level. And that's like the perfect situation for self-supervised learning. You have a task which you can easily generate data, and you need like quite a lot of understanding to do this task. And there is even like some hypothesis on that, the so-called distributional hypothesis, that says in order to understand a word, you have to look at the surrounding words. And often, even if there is a random word you have never seen in before, you can understand the meaning just how it is used in the sentence. So you can understand new words just by looking at how the word is used. And that is, again, what you're trying to do in language model. You're trying to learn what is the meaning of the word just in the way it is used in the context of this. So this is like one typical task of self-supervised learning, predicting some part of your input. In text, that is predicting the future is what is typically done in language models. So you predict the next words, like I live in, then you already know there is like some possibilities in there. In like it can be an article in a house, it can be a city, something else, but there's a lot of things which can't be there. There's typically no verb after. I live in sleeping, that doesn't really work. You can also predict somehow missing parts sometimes. We'll see that later if you do not want to predict at the end, but you just want to predict something in between. You can do a very similar thing also for images. So you can, for example, predict missing pixels. So you can just take the image, take something out of that and try to predict it. In order to have a good prediction of what is missing there, that is a quite good task. Or another example would be coloring. So in order to check what are good colors, if you want to predict that, you need a lot of understanding. You need to know that this most probably is the grass, so that you put in there the green one. Of course, you see that's ambiguous, so like what the color exactly of all the borders might not be super clear, but in generally, again, you need a lot of knowledge in order to do that. That's a good task. There's of course also one challenge in here that there's not the one correct solution. So you have to check how you can train that, because ambiguous outputs, of course, are always difficult. And especially in the image, it might be more difficult because in words, we have more discrete. I mean, there's only like a fixed number of tokens that you can use. In an image, you have all these pixels and the image can get blurry or so. So in self-supervised learning, that's always a danger, that you're just learning to have some, as you said before, for the other example, average, so that you learn some blurry average of a lot of images, and that's like a decent, good solution. But in general, like predicting missing needs to have a quite good understanding of the whole image to do that. Another thing of doing is predicting properties. So that can be, for example, in text, there is a task of the so-called next word prediction, where you say, next sentence prediction, where you say, are these two sentences next to each other or not? Is it the correct order? And again, you need a lot of understanding to know whether one sentence can follow the other or whether they are somehow completely unrelated. Or in image, there's these puzzles where you have to you get this part of the image and this part of the image, and then you have to say how they are related. So that is, so you have this part of the image, and then it can be like top left, top right, and so on. And they are just numbers. So given this image and this image, you have to say how they're related to each other. Again, you need somehow recognize, oh, this is a face and this is the ear. So most probable this is like to the top right corner of it. And finally, another task can be like somehow the relation. for example, you can look at different views on the, so this is original image, this is rotated by some degrees, there is noise to it. So there you can create some type of noisy data, and then you want to either reconstruct it or predict these type of different views of that. All of that is like, so as always, you start with some data, you like somehow change the data that it's no longer everything in there, and then you're trying to predict what is missing with an automatic model. And that is, the successful application of these types of self-supervised learning. Before we are looking at the different architectures, do you have any more questions to this? Good. Then let's have a look at how things are how we can do things. So typically there's like, we'll see 3 different types of architectures, how we train these types of prediction models. But the one thing you can do is you take your input, you put it through then the encoder, you learn a representation, and then of course for your prediction test you'll have to have some type of small prediction model up here, and then you have your label which you're predicting. And so this is your overall architecture, and you're mainly interested in the green, although you're training of course everything from blue, green, and purple. So you have some type of encoder which learns the representation, and then based on this representation you do your prediction. And if you later do a different model, you can replace your prediction by a new one for the supervised task, and then do your supervised learning. There's an extension to that where you might have more power in the top. So maybe representations for your task, you need to have some type of different other additional representations. So the most useful representation in the end is not the top one you had up here, but you're using more some intermediate representation. So what you then have, you have your encoder, you use a representation, and then you have some additional computation here in the decoder and the prediction to then do your final prediction. And finally, we say there's also, again, a bit like what we had before. You might want not to do really predictions, but other things can be that we're also looking into comparison thing. So in this case, you typically have 2 models, and you compare either the representations directly or the output of the decoder to have a comparison here, and then say how similar this representation is, and make then similar representations more similar, for example. So this is more like we had that very at the beginning ones with the Siamese networks who are coming that today. So if you're trying to learn something where things that are similar should be trained in a similar way and the other way around. And these architectures, we want to now look at 3 different use cases. So we'll start with language. There we'll first have a look at what is called decoder-only models. If you remember, we had them in the sequence-to-sequence lecture once. So we'll first focus mainly on the decoder-only models. Then we'll also look at more like encoder-style models and how we can do self-training there. And at the end, very briefly, at encoder and decoder models. The second part will be then we're looking into how we can do this for audio. And the main difference in audio and text is there that text is discrete signals, while in audio we have continuous signals, which makes some things a bit different. And then finally also look at vision models and see how vision models are doing. Okay, before we are now looking at the real examples, how to do things, any more questions about these tasks for training models in a self-supervised way? Good. So let's go back and look at language. And we already said there is this connection to language models And there we first want to have a very brief look at what the language model is. And then we'll see that this is mainly also a self-supervised task, that we are modeling it and that we can use to train decoder-based model. In general, language models have been used before self-supervised training. They were mainly there as an additional feature. If you do any text generation task, you have typically in text generation two things. On the one hand, the content should fit into what the input is. If you do translation, the translation should have the same content as the source. If you do speech recognition, the content should be the same in the audio and the text. If you have a dialogue model, the content should somehow match the question that the user puts in. But besides that, the text should also be good readable to the user. You want to have something, the house is small and small the house is. Those are like content-wise somehow right, but the first one is a real English sentence, while the second one is not really good English. And that is what people are typically modeled by a language model, that you try to automatically learn how a good sentence structure is. So formally, this is typically a function which gives in a sentence and then learns the probability, how probable is that this sentence was produced by a native speaker. And this, of course, includes a lot. This is not only, and that's why it's interesting, it's not only syntax. Here it's syntax, but we had the example with the plane before. The sentence, the plane drives, should have a lower probability than the plane flies. So there's also like semantic information in there. The question is, how can you do language modeling? And of course, the first approach is like if you do estimation, you're doing something like, if you want to look how good the probability of good morning is, you count how often good morning is in there, and then you divide it by how many sentences it is, and that's a good prediction. The problem is there's sparse data, most sentences you haven't seen, so that's why you're starting to do the language modeling maybe as a bit of a different task. So we can't do it just like as a full sentence prediction task. What then comes into help, and now we're getting to more the self-supervised thing, is that we are doing using the chain rule. So we're breaking up the prediction of the full sentence into subparts, meaning that instead of directly modeling good morning, we are modeling how probable is that the sentence starts with good, and then we are modeling how probable a continuation of morning is given that we are good. So that you can do with the very nice Bayes rule. So the probability of B given A is the probability of A given B times divided by P of A. But that means the probability of A and B, so of good and morning, for example, is the probability of good times the probability of morning given good. And you cannot only do that for two variables, but you can do that for any sequence of variables. And that is what we're doing with the chain rule in general. So the probability of a sequence is the probability of the first item times the probability of the second item given the first, and so on and so on. And this gives you now, if you want to have the probability of its water is so transparent, is the probability of its given the probability of water its given the probability of is given its water, and so on. Did we now already solve the problem? Is it easy to estimate this type of probabilities?
It's probably going to be 0 for long sentences because we multiply a lot of probabilities that are smaller than 1.
Yes, that is in general a problem of language models, but here it's even quite sure 0. Because for the last one, in order to model the probability of transfer given its water is so, you would have to have seen its water is so transparent. So you would have to see the whole sentence, and then, like, since most sentences you haven't seen, the probability is still 0. And now we are coming to like a bit the compression, as I said. So in order to estimate these probabilities, we can't always perfectly estimate these probabilities, because there are just too many histories. If you think about 64,000 words, average 25 sentences, then you have 10 to the power of 100, 65,000 to the power of 25. So like 10 to the power of 120 possible histories. And you have never seen all of that. So what you would have to do is, instead of using the probability given the real history, what you can do is replace the real history with some type of meaningful representation of this history and then do the prediction. And this is now where self-supervised learning will come in. So how can we learn this type of very good type of history? Then we can do a good prediction of the next word. Then we can predict very well what is the next word. If we can somehow good summarize how the history is. If you understand what the plane means, then you have a good estimate of what could be following words. So we have to learn this type of clustering in a very good way in our hidden representation. Then we can, and we're learning it by learning to predict the next word. Because what we have to do in language modeling is that we have to learn some of this good type of representation. Initially, that was done very, very simple and worked reasonably good, maybe surprisingly good, with the so-called Markov assumption. So the easiest type of clustering is you cluster the whole sequence only to the last word. Again, based on text, the most surrounding words are most important. So you could just say, oh, we're clustering all the words, all the history only to the last. If you have the plane and predict the next word, you're saying, oh, it only depends on plane and the is not as important anymore. And there you already see, yeah, that makes somehow sense. So the next word, the plane seems to be the most important word of how to continue. And that would be like a bigram language model. So you only look at the most important word. And then the same thing is I mean, you can then of course extend it to 2, 3 grams or 4 grams, but at some point you're again running out of training data or estimation data. So it might not be the best way to do the clustering, but at least this type of clustering where you cluster all the history only by the last 2 words is an initial good version. But now, so this is the main motivation in language models. So what you have to learn is a good representation of the history, and then based on that, you predict the next task. And you have to summarize a lot in order to make this estimation very well. If you have understand what is there and have compressed it in a good way, then you can do this estimation very well. And while the Markov models were initially a decent good step, in order to really do that very well, what you have to do is, you can use neural models for that. And the nice thing is that it looks very similar to what we had before on the neural models. So how you make a neural language model now is that you put in your text, and this is a sequence labeling task. So you make a sequence labeling task, and the only thing is you're shifting your outputs by 1. So at the beginning, you get an empty input, and then you're predicting what is the first word. Then you're putting in the first word here as your input, and you're predicting the second word. You're putting in the third word, and you're predicting the next word. So again, what you're now doing, trying to learn, is here a representation which summarize very well what we have done before, so that you can do a good prediction of the next thing. So what we have here is like the sequence labeling models we had before, where your input is a text shifted to the right, and the output is just the text in there. And that is what is a standard language model that you can train on. And so the architecture is relatively straightforward. So what we have is we can use like a one-hot encoding again of the words. So first we take the words and represent each word by a vector. Then you're learning some type of word embedding to learn a more dense representation already, because you can't work on your neural network with vectors of like 100,000, but you're maybe doing it to 1,000 or so. Then you have sequence layers, for example, in R and N here. And then on top, you have again a classification layer where you then extend the representation from here again to the top. So here you see, of course, there is a big issue in there. The classification is maybe a bit different as we had before. So typically we had maybe 10, 20 classes. Now you have 100,000 classes. so quite a big layer. And we're not really interested often in that. You're only in this. But in general, that's just a normal type of classification test that we have, where we just try to classify the next one. And of course, you not only can use the attention, okay, no, I said it. So you can not only use the RNN here, but you can also use instead there an attention layer. What is important here is, of course, we can only use the mask attention. So we always want to look only to the back, and we cannot look to the future. But we can always look to the back and use that then again as our representation. And yeah, in this case, then the training is also like very, very straightforward in the way that what we're putting in is we're putting in as input the full sentence with the start of sentence token here. Then as output, we have our sentence without the full of sentence, and then we can use cross entropy to do the training. Before we are looking more into now the training, any more questions about this type of neural network? Good. So then let's have a more detailed look at the training. So if you want to train that, this is then English Ersatz, a language model. So we're putting in there the hidden state, and then you're predicting here the output probabilities. So here, this vector here has now your vocabulary size, and what you're doing is you're predicting at each time step, you're predicting what are all the probability distribution over all your possible words. And then your cross entropy loss is that you're looking into what would be the correct. So here it would be the entry for dies, here for ist, here for ein, and so on. At the end, typically you have to predict like this is the end of the sentence. And then cross entropy is a sum over all positions, then the sum of your vocabulary, then what is your reference value times the logarithmic of the output probability. Now, the nice thing is with your reference vector, that's again a one-hot representation. So most values of the t will be 0, so you don't have to multiply that. What you just have to do is you have to only look at the one index where it's not 0. So there's only one correct solution. It's of course not perfectly right, because you have often different ways of extending it, but we are only considering the one we're really seeing. And what you then do is like, so only for the correct one, you're taking the logarithmic of the output probabilities, for the others not. So you can just simplify that as a sum of all the positions, and then the output probability always at the position of the word. So this one, plus this one, plus this one, this one, this one, and this one. And then you can continue the training of doing backpropagation and so on. There's one huge advantage of language models, especially what we see later, is it's very, very efficient. Because you're training on one training sentence, but you're getting a lot of feedback signal. So you're not only getting like, oh, this is the right word, and that's it. For each position, you get a feedback signal. So mainly with one forward pass, you are not learning like one single task. You're not only to predict the third word. You're doing it in the forward pass that you're learning for each position what is like the right one. And that's like one big advantage of this language modeling task, that you get all these feedback signals. So you're directly learning not only that after plane, it should be flies, but also after flies, it should be this word, and after that word, it should be, and so on. So at each position, you're learning this, and therefore, like, yeah, get a very fast type of learning. The interesting thing is even you can like use these types of language models, of course, for generation also. That's not for so much for self-supervised learning, but in generally for doing this type of models, you can also use them to generate. So in inference, it's then the same way. What you can do is like as input, you put in the sentence start, and then you get a probability distribution over all the words. And then, for example, you can take the probability, the highest probability, and get that, and then put that in again and generate and so on. So this is then how you use language models in order to do this type of generalization. So we said in the statistical language model, we said the important thing is that we are summarizing all our history. With you look at more from this neural network perspective, the history means a prefix. So what you have read before. So the question is that also somehow summarized? And so what does the language model do there, the neural language model compared to the statistical? We said in the statistical models, we take only the last two words. If you now think about this more like RNN style language model, how is there the history summarized? Any idea? What is then what is your clustering algorithm you're using there, or what cluster do you use? What is the representation of all the history in an RNN style language model?
It's just the addition of the hidden states, more or less. I mean, it's actually together, no throwing out like in the RNN described.
Yes, so it's a hidden state. So it's even not it's just the final hidden state, as you say. So the hidden state here is like everything, should have summarized everything before, and is used to predict. This hidden state has summarized everything and is then used to do the prediction. And in order to do this prediction is this hidden state, which summarizes sentence start and end. So you're again doing some type of clustering, but this time it's more continuous clustering. So you summarize all these histories in this like fixed size vector, which of course might also like at some point get a problem because you have to always summarize into a fixed vector, and that's getting challenged. What about the mask self-attention? Is there done some summarization, or how is it there put together? What is done there? Any idea? Yes?
By definition, yes, it's the summarization of everything which is not masked yet. So yeah, once again, the more or less hidden state.
Yes, so it's a context vector. So what we're doing in mass self-attention is we're doing taking this key, querying all the previous hidden states, and then we're doing the weighted sum with these weights and our values. And this is the context vector that we're using to do the prediction. So again, we are summarizing everything into one fixed hidden state, and we're using that to do the prediction. So we're somehow doing a very similar thing than in the statistical language model, just that we have a lot better like learning in there. And that is the main thing we're interested in, of course, for other tasks, that this is a very good type of representation. There's also still there is a difference between an RNN and the context vector if you now view it as like how things are summarized. And in that way, maybe the context vector is a lot more powerful in transformers. Any idea? Yes?
For the context vector, just what is important, and for the RNN, just everything thrown together.
Yes, it's more about the building process. I mean, that's also right, but to understand it, maybe it's good to view it from the building process. Yes?
There's no information decay.
Yes, so yeah, maybe you can formulate as there's no information decay. So once the hidden state at position 6 is based on the hidden state at position 5 and the new input, and you're combining these two together, while in order to build the mass self-attention, you always look at all the previous ones. So there's not that the last one decay, as you say, or like they are not that strongly connected. You're free to always build new summaries in doing that. How much information is encoded is in both, of course, are like the limit by the network structure is, of course, in both there. We have in both cases a hidden state of a fixed dimension where we have to store all the information in order to do that. So yeah, to summarize the neural language model, what it is doing is the input is always a prefix, and then we are predicting the next word. But it's very and then that means what we always have as our representation is a prefix that is all the words in the left context. What is a big advantage is that we're not having to do that like one example by a time. It's not we're giving a prefix and we're predicting the next word. Then we give another prefix and predict the next word. We give another prefix and predict the next word. If we're doing it as a language modeling, we can do that all together and predict all words in parallel. And then you don't have to recalculate always because of course prefixes overlap significantly. The prefix of in and of Karlsruhe are mainly the same. It's just like one additional word. And that is a lot of the efficiency of training language models, that you're not always view it as a prefix and you're predicting a word, but you're directly predicting all the sentence where you do that then in parallel. And if you look back at the architecture, where we mainly we take as input the prefix, we encode it, and our label is then the next word that we have. Good. So this is a neural language model. We're using that a bit again when we're talking about, large language model, especially prompting, because the difference between a neural language model and a large language model is only the size of the model. That's exactly how large language models are trained. But yeah, before we're going there, do you have any more questions to this? Good. And then we want to look at the other types of text encoders that are also interesting. So what we had until now is that we only represent the left context. But if you really want to learn a good representation of, let's say, Karlsruhe in this sentence, it might be good to have a representation of the full sentence and like learning what Karlsruhe means in this full sentence, and not only look to the left, but also to the right. So what we would like to learn is like inside this representation here, the green one, it might be good if it's not only represent what was before, but it also might be helpful to know what was happening after. So we can learn a somehow better representation. And how this can be done, you should know by now. It's like with like bidirectional models, there can be a bidirectional RNN, or if you just use a self-attention network. So instead of doing mass self-attention, you do just normal self-attention. So can we now extend what we did before and just train a model and replace the RNN by a bidirectional, or train a normal self-attention in here? Or do you see any problems when we're doing that? Yes?
We could do a similar approach and just mask some words in the sentence and try to predict them, but then we don't have the benefit of predicting the entire sentence.
Wow, you're 3 steps in advance, but it's exactly right. Just do 1 step back. If we're just doing it without masking, it wouldn't work, because then you have this loophole what we had before. So if you would just take here a normal prediction and try to predict in, what the model would learn is, oh, you always have to put attention to your next word, and then you can predict it easily. And that's why without masking, we're coming to what masking is. So without removing this in from there, it doesn't work, because there is this simple solution. And of course, you can train the model. The problem is you'll have a very low loss, and your representation will not be very helpful, because you want to learn a representation here that represents what the word live means within the sentence. What you will just learn is, oh, this will represent in, and that's it. And you have no, sensible and good representation. So we have to change anything. If we want to use also the future context, we can no longer predict the future context, because that is already there. So what can we do instead? And you mentioned that already. So the idea is, yeah, if we want to predict like things from in a bidirectional way from the back and the future, what we're doing is we just have to like delete an input, for example. We have to delete this word and then try to predict what this word means. And this was, or maybe still is, a very, very powerful pre-training for a lot of models which not try to generate text, but which try to more do natural language understanding to encode the text. The main or the most famous version of that is the so-called BERT model, which is a bidirectional model which tries to do this as a bidirectional model to do then masking. So it masks out some part of the sentence and then tries to predict these types of words. It's was maybe one of the first models which heavily relied on self-attention in there. And in addition to masking, it also has input of several sentences, or typically two, and then it does this, what I said, next word prediction. So it also learns a classifier which tries to predict whether these two sentences are the same or not. The nice thing is you have these extra token, and that you can, let's try to learn more a general representation of the full sentence. So besides learning a hidden representation of each individual token in the sentence, we also learn a representation of the full sentence, which is then helpful for other tasks if you want to do more sentence classification or things like that. So let's have a bit more look on how the model exactly is trained. So then people then called it a masked language model because, yeah, if we're doing a bidirectional model, as said, we can't do like next word prediction. So instead, we have to mask some subwords, some words. And of course, now it's getting difficult because you can't mask everything. If you mask everything, there's no information anymore. So there starts to the hyperparameter tuning, which is difficult. So what is typically done is that 15% of the data of the words you're removing from your input. So maybe again, similar to the denoising autoencoder, you put in your input and you, for 15%, you say, okay, this one's we are removing. And then for these mask tokens, you're doing different strategies. So for 80% of them, you're putting a specific token saying this is masked. For 10% of this 15%, you put a random other token in there. And for 10%, you're doing it unchanged. And then in the training, and that's now, as you said, the disadvantage, now it doesn't really make sense to predict all the other tokens. So your loss is only calculated on this 15% where you have which you have replaced. So you're no longer getting now a feedback signal of 100% of your tokens, but only of 15% which you removed. And therefore you do one additional task, and that is the next word prediction, the next sentence prediction, sorry. What you mainly do is you're predicting whether two sentences are consecutive or not. So you have, for example, this sentence, the man went to Ma's store, he bought a gallon of milk. These are two sentences where like that makes sense that they're after each other. So here you train the label as is next. And then you have the man masked to the store, penguin are flyless birds. It doesn't have any connection, they're just randomly sampled. So in this case, you label the one as not next. And you see, you also put in directly the masking, because then you at least can train that together. You're not having to train one the next word prediction and one the other. What you're doing, and the question is, how do you predict now the next token? This token, you have an additional word, the CLS word, an artificial one at the beginning, and based on that hidden representation, you're learning that. This is a very nice advantage, that for this token, the hidden representation you are learning is somehow a summarization of your old input, because you need everything about your input to learn this classification. So here you're not only learning a hidden representation of each individual word, but you're by this additional task, you're automatically also learning a representation of the full input. Yes?
How to make sure that the label not next fits, because even if you choose random sentences, you could still by chance use two that fit. So do you use a classifier to do that, or?
No, that is just noise that is happening there. That is similar to what we also do for the missing word prediction. So in the missing word prediction, we're also only saying the one word which occurred there is right, and all the other words are wrong. I mean, if you have the cross entropy loss, what you mainly say, this is the right word, and all the other words are wrong. Because if you train it with softmax, you're putting all the mass to that one and trying to reduce mass from all the others. And that is, of course, also not right, because when we have the plane, flies is a good, but arrives is also a very good solution. Still, if you're seeing that, you would harm it. You're somehow preventing that by training about a lot of examples, and then the correct one should occur often, while the other ones very rarely. Yes, I think there's still. I mean, you can't really do label smoothing. You have only two labels, next or not next. So I think there's no sense in doing label smoothing. It's more that since you're averaging over a lot of examples, you're getting things out. Yes, so the whole model looks like this. This is like the pre-train. So what you put in is you put in pre-training, you put in here your masked sentence 1, the first one, and the masked sentence 2. And then you're embedding them. And then you have here a lot of self-attention layers. And then you have here up your prediction. And you do your masked language modeling task, where for all the masked tokens, you predict the right token in here. And as an additional loss, you have the next sentence prediction token, where you say whether this is the next sentence or not. And this way, now this BERT model internally here can have a normal attention where you do it in those directions, because you're predicting only the tokens that you haven't seen in input. At the cost of that, yeah, you only can do that for 15% of the tokens and not for all the tokens that you have. For bidirectional models, they are typically also called like encoders. Then you can do bidirectional processing. Of course, I mean, the nice thing is if you do bidirectional processing, you have more information, but of course you can only do that for models where you have all this text available. So typically only if you want to understand the text. If you want to generate text, you can't do that because you're also generating text by text. The loss is a masking loss then, and there's a lot of examples. You see people are very creative. So it started with birds, and then there was Roberta and Albert and a lot of different models that are all trained in this way in a self-supervised way. Any questions to this? Good. Yeah, then you can even also do things for sequence-to-sequence models. So we said at the beginning we have these sequence-to-sequence models where you have an input sequence and then you want to generate an output sequence. So typically you had a bidirectional encoder for your input, and then you have an autoregressive decoder in order to generate that. And of course, there you always need input and output sequences. However, there is also like the so-called BART model, which now tries to do that, where the input and the output sequence is the same, again, in the way that that you can do things, learn a good representation if you want to use an encoder-decoder model. How you're doing is that you're again adding noise to your input, and then you can generate it directly in an autoregressive way. Of course, the problem is, again, if you have put your input here, learning an autoregressive model would be super simple, so you can't do it. So they introduced then different types of noises, so 5 different types of noises. So the one is, again, that you do token masking. then they also, instead of masking, doing deletion. So the difference between them, here you put an extra token saying, oh, there should be a token, but I don't know it. While here you say it's just A, C, and E. So you're not telling that there is a missing one. You can change the order of the sentence. You can completely rotate it, do text infilling, and then, yeah, all of that can be added here. And always the correct sequence is, of course, always the correct one in there. Yeah, the difference between text infilling and masking is that you're not replacing like a single token, but a longer sequence of that. But yeah, so in training, it's very similar. Like from the data augmentation strategy is very similar to BERT, just a bit more extended. But now you can then generate also in an autoregressive way. Still, the problem is that, of course, you have some input in it, so it's not as clean as a task as a next word prediction, where there's no information from the input to the output. Good. Any more questions to this type of? And yeah, so these models were of course very successful, and that's why very similar approaches are also used at different modalities. And we want to look at one example from audio, and then some ideas maybe at the end or next time for image. So for audio, maybe the most important one is the so-called wave to VAC. And there again, the idea is, can we learn, if we now put in here an audio sample down here, can we learn a good representation for this audio sample in there? And so we again do the masking. So or you want to have a bidirectional model. So you're just cutting out some audio here in red and then trying to learn a representation, which is good. Of course, a bit more difficult is in here is like, how do you predict the missing input? Because it's like continuous, and predicting continuous, it's maybe a lot harder and not as straightforward. And furthermore, you want to also downsample. So audio sequences are typically quite long. So typically, even if you do like normal audio processing, it's maybe 10 times longer than the character sequence. So in order for a further model to have a good representation here, you want to have this representation to be shorter than your audio sequence. Then again, it's a question how you can do that. And we'll see they do it with some type of downsampling here. How downsampling works, you should maybe remember. Anybody remembers how we can downsample the length of the audio with a neural network in the encoder? Yes? Yes, exactly. So you can use a convolutional thing here, which then like strides not by one position, by several positions, and then you reduce your length. Then you get a more compact representation. The question is, how do we then do the prediction? And that is a bit done differently for this type of continuous signal. And so the idea is you have first the pure feature encoder, which is CNN-based models, which learn a first representation. So they have more only local context because you only have your window in there. And then you get these first part of hidden representation, and the red ones are the ones which got masked out. So there we are. And then you get here your representation. You do a clustering, so you can just do a clustering of that. So then you get a code book, meaning you have now discrete representations here for all of them. Then on top, you have a context encoder, now taking the whole context in it, meaning mainly that is a self-attention layer. So here you have several self-attention layer, which don't change the length anymore. And now you want to learn somehow here meaningful representations of that. And that is done by two types of losses. So first, this type of discrete representations should be somehow meaningful. And meaningful is like, one important thing is that they shouldn't be all the same. Then the predicting this type of codebook would be easy because you always predict the same one. And that's why they have a diversity loss saying that, yeah, the representation within one sequence, they should not be all the same, but there should be some difference between them. That's the first part of the loss. And then we have a contrastive loss saying that at this mask position, this representation should be similar to this one and dissimilar to the others, and for the others too also. So you're now trying to predict the missing ones, which you mask afterwards, again, and you're trying to make them similar to the ones which you initially had here and dissimilar to the other. So you have two types of losses in here, the contrastive loss, which make them similar, and then the diversity loss that you really have meaningful representations in them. And by doing the clustering and not directly predicting the hidden representations here, but the clusters here, you're a lot more robust because you don't have to, like similar, you're forcing that similar representations first get to clusters into somehow a meaning or phoneme style things, so what was said, and then you're trying to learn things there. Any questions to that? So again, you already see, in the self-supervised way, this type of preventing this loophole is challenging. You can do that masking also to get a good feedback signal, especially for continuous one, is more challenging, and that's why you introduce some things like codebooks where you try to cluster things in together and then just predict the cluster and not the individual hidden representations. Good. And then for the last 15 minutes, what we want to look at is then how things are done more in image processing. Again, the ideas are often very similar, that you have to address for some specifics to them. And we'll have a look at some examples there. One example is here, the context prediction. We had that mentioned at the beginning. So the idea is here that you try to predict the relative location of two parts of the image to each other. So again, if you take this image part, you to try to predict whether this is like top right, lower right, and so on. So your main task is this is your two inputs, and then your classification that as if you want to process two images, two inputs, what would be maybe a good network architecture? Had that today already, maybe an hour ago. So anybody remembers? So the last architecture we hadn't covered really today, and that's this parallel architecture. So that can be used here. So we're using this type of series networks where we have like our neural network here, and we're putting the two parts of the image that we had through these networks. And we're trying to predict them the same, like process them the same, because really we want to extract what is the information you have here and what is the information you have here. And we want to learn all of that in parallel. So we're applying the same network twice to the two different parts of the image, and then learning here a representation. And this representation should somehow like encode what is the most information in there and there. Then we can concatenate these two representations. So we have information about both of them. And then we can do here our classification, 8-way classification, because we have 8 times of rotation. And then, of course, this representation here, this yellow one, is the one we're really interested in, and that we can then later use for images. Hopefully having encoded the main content of that in order to do the right type of prediction. A different version of that is this jigsaw puzzle or unsupervised learning of visual representation. So there we are just directly doing all of that together. So you again take the 9 parts you have, take them as input, then you shuffle them randomly. And for this permutation, you're calculating maybe a number or storing a number. Maybe this is like index 64. And then what you want to do is like predict the shuffle index here at the end as 64. And again, each patch is processed the same way. And then we have some additional processing to learn which permutation it is, and then you do it. Again, this time you're not learning just like 2 examples, but you're putting in all 9 in there in parallel, then predicting which type of rotation that is. Again, in order to learn, what is the orientation of the different types of network. Any more questions to this type of permutation-based examples? Then another idea is, and again, it's often good to have like different types of things, is to do like the coloring. So you put in the grayscale image and try to predict the color of that. Again, of course, that it might be ambiguous at some point, but you should have a good understanding and see what is happening. This you can do also with just a normal neural network. So you put in the image, then you're doing some convolutionals in here. You see always it's like 256 dimensions, just represented in different blocks, so that you have information flow over them. And then you're trying to predict the A and B values so that you then can reconstruct with your grayscale information the full image at the end again. So again, like just a different task, we're training the full model in order to hopefully learn a good representation of the model, because you have to use this information, or you have to understand where the different colors are. Then there is the idea of rotation. So that is like a 4-way classification task where you try to predict the rotation of an image. So you get an image and then have to predict this is a 90-degree rotation, 250-degree rotation, 180-degree rotation. It's correct one. It's also 270-degree rotation. Again, I guess you need a lot of understanding to know in which rotation the image could be. Might not be always perfectly solvable again, so maybe sometimes there is EV2, but for a lot of these images, I guess you would have correctly identified them. So again, it's like a task where you might need a lot of understanding in order to do that right. And then, of course, we saw the masking is helpful for language. So that might be also good for images. So if you have a way to predict what to put in the image, that might be also a good point. And that's the infilling we're coming into then as last, where again the idea is, we have to correct the image in order to do that. Might be for images a bit more difficult because you can be blurry and so on, and what is the right, but in general you can do the same thing. So you can do that with masked autoencoders. So the idea is here, you map the image into patches. Then you encode each of the patches that you didn't mask, so less. You have the encoded, you put them into the full image. So you tell the model where these patches were, and then you have a decoder which tries to generate the full image in there. Meaning that now, of course, you have to, for this model, I guess there's so much scaling that's even difficult for us to recreate that. But again, that is the task of trying to predict what was all done there. In a bit, the challenge is there. If you now do pixel-wise, is that the correct value or not? These models sometimes tend to generate blurry images because they are in average always good, and that might be a challenge. But in general, it's very similar to the text. You also remove information from your input and then trying to predict these informations back in there. Here you see that. So you have your input patches. That is what was predicted. You're seeing it's not perfectly what is the right image, but maybe surprisingly good. I'm not sure if I would have done it in a similar way. So there's a lot that can be reconstructed. another example here is the in-painting, similar idea. So you have a CNN encoder, you encode it here, and then you're trying to generate it out. The problem is here is it's a bit like blurry, and that's why people try to add additional losses now in order to prevent this blurriness and really try, because maybe with the MSE loss, if you just do the average, you're getting in the end this average of the different possible solution. How can you do that then? So there's like additional things to do. One idea is to have an adversarial loss. So what you do is now you do the reconstruction loss, but in addition, you train a classifier which classifies whether this is a reconstructed image or the original image. And if your reconstructed image now always generates blurry things, that's a very nice indicator for this classifier. Oh, that's a reconstructed, and you will get a very bad loss on that. So by this additional classifier, which tries to classify whether it's reconstructed or not, and you use this information in order for your model to predict an image which is indistinguishable from the original one, you have an additional like force to make really good type of images in there. So again, the idea is, yeah, maybe we need more feedback signals than just the pure like reconstruction. You can also have additional adversarial loss to do that. Another one is also to do contrastive losses. That is for the last part where you have different types of views of the image. So what you do there is you have different views of, for example, the dog. Once you have a cut, like some part, and sometimes you have the grayscale image. So you just do different versions of the same image, put them to the representation, and then you're trying to learn that similar like image from the same original image should be as similar as possible, while representations from different images should be as far similar as possible. In this contrastive loss, of course, there's always the problem of what do you use as similar images and what do you use as non-similar images. For example, in SimClear, that is then used that we just use the negative examples within your batch as all the negative examples. So you have to enforce that in your batch, there's always two which match to each other, and all the others are negative to each other. So yeah, what is an additional interesting thing is here that again, here is what we had before, that it might not be good to use a final hidden representation, but you add some power to learn representations, to learn things which are only important for distinguishing the images, but not really good representations. So you have the decoder on top of that. And then you're mixing your images. So you have a green and a gray. So two of the same image. This and this is the same image. This is the same image. You encode them in your batch. So always the gray and the green one are from the same image, and the others are others one. These two map together. And then you get this matrix where these two images are from the same image generated and all the others are negative. And of course, on the diagonal, you have your own image. So in total, you can then train the model by making in this case, is making the representations more similar, and by all the white ones, making them more dissimilar. Again, this is the idea of like trying to train it in a way that similar things get together and dissimilar things get out of them. And with this, we're at the end. Any more questions? Good. Then, yeah, I hope you got a bit an idea of how you can train self-supervised in a way. And there's, of course, a lot of ways still to explore. Then on Thursday, there is a day off. And then next Tuesday is a practical session. And next Thursday, we'll then have the next lecture.